All right, hey guys. Today we are going to actually start our next topic. And so what we're going to do is really look at we're kind of going to go back to alkanes and alkenes, which we kind of looked at a little bit previously, but now we're kind of moving on to the triple material. So I just want to reiterate some of the points that we made about alkanes, introduce alkenes, and do something called isomerism, which you've never heard of before, but we'll have a go at that. And then finally look at some chemical reactions that alkanes and alkenes do. So today, what we're going to look at is sort of like what is organic chemistry, and kind of define a homologous series in this video, and then in the subsequent videos we'll kind of look at other stuff surrounding this topic. So for this video we'll just look at organic chemistry. And homologous series. Okay, so a homologous series is literally just a group of compounds, organic compounds, that have the same sort of properties. We looked at this before. There are some specific things that we need to kind of know about homologous series. So if an organic molecule group is a homologous series, the following things will be true. There is a general formula. General formula. The size of the molecule increases by CH2 as you go down the group. They have similar chemical properties. There's a gradual, can't spell today, gradual change in physical properties. So these are how we know that something is a homologous series. It has to follow these rules. If it does not, then it is not a homologous series. When we talk about organic chemistry, it kind of makes you think about natural things or things in nature. That's not what organic means. It's certainly what it used to mean back in the day, but today organic chemistry is just a study. So organic chemistry is the chemistry of compounds that contain carbon. Now we call it organic chemistry because the compounds of life all contain carbon. Things like proteins and carbohydrates and fats and all these things, they all contain carbon. So that's how it got the name organic chemistry. We just sort of expanded that idea of what organic chemistry is over the years. So it's really just the study of carbon and compounds that contain carbon. Now the simplest homologous series, so simplest compounds containing carbon, are the alkanes. alkanes are the simplest of these carbons, of these carbon-containing compounds, these organic molecules. See, the alkanes all have a general formula, which, if you remember from before, is CnH2n plus 2. That means whatever the number of carbons there are double the number of hydrogens, but you need to add 2. So for instance, if I have C6, then I'm going to double it. 6 times 2 is 12, and add 2. That makes 14, so my H will be 14. If I had C10, well, then I need to double it. 10 times 2 is 20, plus 2 is 22. So I have C10, H22. It's as simple as that. It's really not difficult to understand. It's just a simple formula for working out what the formula is. Okay? They go up in CH2 each time. Well, let's have a look. If you remember my, if you look at the actual homologous series, we've got methane, ethane, C2H6, propane, C3H8, butane, C4H10, pentane, C5H12. I hope you can see that every time we go up this list, we're adding CH2. Every time we go down this list, we're adding CH2. So this definitely follows the second point about homologous series. If we just scroll up to see those, look, there's a general formula, and the size of the molecule increases by CH2 as we go down. So that is definitely true. Now, I can't show you this, but they all do exactly the same kind of chemical reactions. These actually don't really do chemical reactions. So alkanes are very unreactive, but are very easy to burn. All alkanes are really like this, so then they all have very similar chemical properties. As I'm sure you know from last time, their viscosity as we go down gets thicker, their boiling point gets higher, so we're showing a gradual change in the physical properties as well. So as we go down, they become more viscous, they become less flammable, they become less volatile, and they have higher melting points and boiling points. So we're seeing a gradual change in the properties as we go down this group. So here we go. That is the alkanes as a really good example of a homologous series. One of the things you'll have to be able to do with the alkanes is you'll need to explain what the different alkanes actually look like, and you may need to be able to draw pictures of them. So let's have a go at drawing these out in what we call displayed formula. If you remember, a good way of remembering the first few compounds of the homologous series of the alkanes is monkeys eat peanut butter, which is methane, ethane, propane, and then butane. These are the first four elements of the, not the first four elements, sorry, the first four compounds in the homologous series of the alkanes. All the rest of the alkanes are easy to name, as long as you know how to name shapes and stuff, because it follows the same rules. After butane, we have pentane, which means 5, then hexane, hex means 6, then heptane, see hept means 7, then octane means 8, nonane means 9, and decane obviously means 10. So these are the first 10 compounds in our homologous series of alkanes. Right, so let's draw those. Again, remember, it's just CH4, and whatever the number of carbon atoms is, the next one down is going to be 2. We just double it and add 2. So C2H6. Double 2 is 4, plus 2 is 6. C3 for propane, it's going to be H8. Remember, double it and add 2. C4, H10. I'm sure you get what it is now. This is going to be H12, just doubling it and adding 2 each time. C6, double 6 is 12, add 2 is 14. C7, H16, C8, H18, C9, H20, C10, H22. There's all the formulas. Right, so we call this chemical formula. It's just what the formula of the compound actually is, like what it really is. If we draw it out altogether, so this is the name. Chemical formula. Let's do the next one, which is we're going to have a look at the displayed formula. Now, when you're doing displayed formula, you have to show every bond. So methane would be this. 1 carbon and 4 hydrogens around it like this. You're showing every single bond in the molecule. For ethane, you want to draw the 2 carbons first and then put the hydrogens on like this. So this is ethane. For propane, again, draw all your carbons first, draw the 3 carbons, and then add in your bonds. Remember, each carbon atom can have 4 bonds. So if your carbon atom doesn't have 4 bonds, 4 lines attached to it, that is incorrect. Right. And butane obviously will have 4 of these. Like this. I won't do any more because it would just take up a lot of time and I'm running out of space. The other way you need to be able to draw these is you need to be able to do a ball and stick diagram. Now, in a ball and stick diagram, you're drawing out the atoms as tiny little balls. So methane looks like this. The black balls represent carbon, and the white balls represent hydrogen. For ethane, we're going to have 2 black balls connected, and then obviously we will have our 6 white balls there, 3 on each carbon atom, just like it's drawn here. For these, you just kind of want to follow whatever the structure is of the displayed formula that you've drawn, and kind of show exactly what it is, but drawing it kind of in little blobs like this. There's my propane. See, I've got 3 hydrogens on the first carbon, 2 hydrogens on the second carbon, 3 hydrogens on that last carbon, just like it is on here. And then finally this butane. We'll quickly draw that to give you an idea what that's going to look like. There we go. Boop, 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 doop, doop, doop. There we go. There's our lovely drawings of all of our molecules there. All right, so let's just look at the chemical reactions of alkanes, and we can really finish for this bit about alkanes. So, I said already, the chemical reactions that alkanes do are pretty much limited to just combustion reactions. So they only do combustion reactions really. So we can only really focus on those things. Now, in combustion, if you remember, we always need oxygen as a reagent. So if you're drawing this, you're drawing a combustion reaction, they normally won't tell you that you need to put oxygen in. They rarely put that in the exam. They just say it will burn in air, or they do a combustion reaction of one of these. They won't tell you oxygen's in there. You have to remember that you always need oxygen for a combustion reaction. You have to remember that. And so, say if we're doing combustion of propane, C3H, what was it? Double it, add 2. Double this is 6, add 2 is 8. Plus oxygen, I need to make sure it's in. What were the products of this reaction? Can you remember? It's carbon dioxide and water. So, this doesn't balance, but this is correct. If you wrote this out without balancing it, if this was all you wrote, you'd get most of your marks. You'd only lose 1 mark. There's only 1 mark for balancing the equation. So what I will always say is learn what the actual chemistry is first and then worry about balancing it. Too many times people try and balance it first without knowing what the chemistry is. That's a really stupid way to go about doing this, and you'll end up with no marks. If you learn that every time you do a combustion reaction, you make CO2 and H2O, and you always write that down, you're going to get 1 of your marks. And if you remember it's the fuel that burns with oxygen, you're going to get a second 1 of your marks. So normally for a balancing equation, there's 3 marks available. If you remember all the reagents, then you can probably get 2 of those marks. And the last mark will be for doing all the balancing. But let's have a go at balancing this. You might want to pause now and have a go at balancing it yourself, and then we'll go over what I'm going to do. Okay, hopefully you've got your answer written down. Let's have a look at what we're going to do then. See here I've got 3 carbons. Well, that means there must be 3 carbons over on this side. So the only place there's carbon is on carbon dioxide, so I'm going to put a 3 there. What this now means is that there's 3 carbons, but there's 3 O2s as well. There's 3 of everything. You can kind of like imagine this as like there's like a little bracket around it like that. There's 3 of everything inside my bracket. It's really what I'm saying. Although we don't draw those brackets in, so don't put those in the real thing. I'm just going to erase them to make sure that you don't make the same mistake. So we've got 3 carbon dioxides there. Right, let's check over here. I've got 8 hydrogens. Now the only thing with hydrogen on this side is here. We've got H2. But wait, there's 2 hydrogens in every molecule of water. So I can't write 8 here. That would be wrong. So we can't have that. Instead, what we need to be writing is 4. Because of this 2, if I do 4 times 2, that's going to equal the 8 that I've got over here. All right, let's count up all the individual oxygen atoms I've got on this side. So here I've got 1, 2, 3, 4, because I've got 4 lots of that oxygen. And here I've got 1, 2, 3, 4, 5, 6, because I've got 3 lots of O2. 3 times 2 is 6. So I've got 6 here. I've got 4 here. In total O atoms is 10. Now over here, this has to be the same. My O atoms equal 10, but look, there's an O2. So that means to get 10 O atoms, I need 5 O molecules. And then I can just remove my working out. Let's get rid of this. And that is the correct answer. And if you follow this procedure of just doing the carbons, then the water, and then the oxygens at the end, you'll always get this correct. Now, Let me tell you something sneaky, because you might not notice this. It could be quite difficult. If I do the next one up, if I do C4H10, let's see what happens here, because you might find that we get a little bit of a funny answer. Still exactly the same. Exactly the same chemical reaction. All chemical reactions are pretty much exactly the same in a homologous series. The only thing that's going to be different is that we're going to have different balancing numbers. 4 here, I'm going to put a 4 there. 10 here, 10 divided by 2, that's going to be 5. Let's count up the number of oxygens. I've got 1, 2, 3, 4, 5 here. And 1, 2, 3, 4, 5, 6, 7, 8. If I add these together, I've got 8 plus 5. Well, 8 plus 5 is 13. Now we have to do 13 divided by 2. But look, it doesn't divide evenly. Well, this doesn't matter. You can have a half. So the number of atoms that this will be is 6.5 oxygen molecules. 6.5 oxygen molecules is 13 oxygen atoms. And yes, you can have half a molecule in your balancing numbers. That's because this relates to the moles, not the actual physical molecule. All right. Thank you very much, guys. And just click on to the next video where we'll talk about alkenes.